Hello, and in this series of videos we're going to be looking in more detail at passive components. The sort of components that we've seen before, resistors, capacitors, inductors and diodes, but this time looking at the behaviour of actual real components that you can buy rather than the ideal behaviour that we see in simulators. For example, we know that the complex impedance of a capacitor should decrease with frequency. However, if you actually measure a real capacitor, it's likely to do something more like this. As you can see, it starts at low frequencies, behaving like the ideal capacitor. The behaviour of the ideal capacitor here represented by the blue dotted line. But at around 60 megahertz or so for this particular type of capacitor, it goes through a minimum value of complex impedance, and then it starts to increase again. And at very high values of frequency, the complex impedance is actually increasing with frequency, which is the behaviour that we would expect of an ideal inductor. So, what's going on? Well, what's going on is that you cannot make perfect capacitors. Any capacitor will have some leads attached to it, so you can solder it into a circuit. And leads are straight wires, and straight wires do have a small value of inductance. So once you get up to a very high frequency, where the effective impedance of the capacitor is tiny, negligible, it's the impedance of the inductance due to the wires which dominate the complex impedance of the component. If we want to design circuits that work using these real components that you can actually buy, we have to take account of these non-ideal characteristics of real passive components. And the most common way of doing that is to use an equivalent network, but an equivalent network that represents the behaviour of a real component across a range of frequencies. For example, consider this top network here. This is an equivalent network for a capacitor. Simulating with this, with an ideal capacitor, two ideal resistors and an ideal inductor, gives you a quite good approximation of the behaviour of the real capacitor across a very wide range of frequencies. All you have to know is the values of these three so-called parasitic components. We have an inductor here, which will dominate the impedance of the component at very high frequencies. We have two resistors here. This resistor, Rp, is a leakage resistor. All real capacitors do allow a very small amount of charge to actually flow through from one terminal to the other terminal. An ideal capacitor, if you remember the barrel analogy with the rubber membrane in it, an ideal capacitor doesn't let any charge flow from its top terminal to its bottom terminal. The rubber membrane is completely impermeable. However, real capacitors do have a small amount of current that will flow actually through them. You can think of the rubber membrane as having very tiny holes in it, which allow some of the charge through. And there's a series resistor, which represents the resistance of the capacitor terminals and the material the capacitor is made of. Without that component there, without the series resistor, then the impedance of the capacitor at a particular frequency, known as the resonant frequency, would be zero. If we go back and look at this graph of the real impedance against frequency of a real capacitor, you'll see that there is a minimum value there. And that minimum value occurs where the complex impedance of the capacitor, the ideal capacitor in the model, and the complex impedance of the parasitic inductor cancel out. But it doesn't go down to minus infinity. The real impedance is not zero. And that is due to the fact that there is this series resistance here, Rc, which gives a minimum value that the impedance of the whole capacitor can have at any frequency. Once you've determined these parasitic components, you can then use this model in simulations and check that your design is going to work with the real component. The other network down here is a network model often used for real inductors. It has a series resistance here, which can be quite large for real inductors, and a parallel capacitance here, so that at very high frequencies, the impedance of an inductor, a real inductor, actually decreases with frequency. Because at those very high frequencies, it's the impedance of this parallel capacitor which is dominating the impedance of the whole component. It is smaller than the impedance of the inductance and the resistance, so most of the current flows through this parasitic capacitance. And a graph of the complex impedance of a real inductor against frequency would have a maximum value in it. In both cases, the minimum value of the impedance of a capacitor and the maximum value of the impedance of the inductor, they occur at something known as the resonant frequency, where the impedance of the capacitance and the impedance of the inductance cancel out. In terms of modelling passive components, this is what the task is about. Working out what these equivalent models are, the equivalent models using ideal components, in such a way that the total behaviour of the model reflects the behaviour of the real component. That's a very quick introduction to the subject. In the next little video, we'll have a look at applying it to resistors.